one, we have f of t equals 2 cosine t plus sine 2t on the interval 0 pi over 2. This is a situation in which we are given the domain. So in this case, we do not have to worry about the domain. So this is f prime of t, this is f of t, and this is 0 pi over 2 carved in stone. So no worries there. We go ahead and we find f prime, and this is 2, negative 2 sine t, and then plus cosine 2t times 2. F prime of t being undefined? No. These are not tangent, cotangent, secant, cosecant. Sine is defined everywhere, cosine is defined everywhere, so no undefined situation. So now we want to find if critical numbers exist from f prime of t equals 0. Good. So then we have 2, negative 2 sine t plus 2 cosine 2t equals 0. Yes, first I will simplify, dividing both sides by 2. And then I have to dig deep and remember what cosine 2t equals to in terms of sine. Because there are 3 formulas for this, 3 identities. But I want the one that specifically has only sine in it. So negative sine t. Anyone remembers this in terms of sine? Anyone? 1 minus 2 sine squared t. So cosine double angle has 3 identities: cosine squared minus sine squared, 1 minus 2 sine squared, or 2 cosine squared minus 1. But we want this specific one. Why did I choose that? Because I only see sine in this equation. So plus 1 minus 2 sine squared t equals 0. Too many negatives, you know, I don't like that, and then it's not arranged in the correct order. So now I will have 2 sine squared t plus sine t minus 1 equals 0. At this point in calculus, yes, you can factor, but you can also, this is quadratic, you can also do this. I'm not forcing my calculus students to use the Corati formula or factor if it's a quadratic simple situation. Go to apps, press 9, go to polynomial. It's not a polynomial, but I can find the solutions in a blink with a quadratic, and this, the coefficient is 2, and the coefficient is 1, and the coefficient is negative 1. So it should give us the solutions in a blink, and they are 1/2 and negative 1. So I know that sine t equals negative 1 and sine t equals 1/2. I'm fine if you just, it's too easy. It's easier to factor than plug it in, but it's fine. So let's solve now. Sine t equals negative 1 and sine t equals 1/2. Remember, we are talking about the first quadrant. So this does not belong in the first quadrant because it would be t equals 3 pi over 2. But 3 pi over 2 is not in the first quadrant. Can anyone tell us the t in the first quadrant such that sine t is 1/2? It's the smallest angle we work with. Nobody remembers the smallest angle we know.
Pi over 6.
Thank you very much. Thank you. All I need to do now is find the sign left and right, plug pi over 6 in the function to find the value. So I can do that with the graphing calculator quickly, because I want to determine and make sure I find not just those values, but what they represent. So I plug in the function to cosine t plus sine 2t. That's the function. And now the derivative. The derivative was negative 2 sine t, and then plus 2 cosine 2t. So the first one is the function, the second one is the derivative. I'm looking at the derivative first. Okay, in the derivative I can even plug in 0. It doesn't matter. So I'm going to make sure that the mode is in radian mode. Good. And I want to plug in 0. 0 for the derivative. Okay, so it's positive. And then I want to plug in pi over 2. Why not? And I see it's negative. And now in the function, I must plug in 0 and pi over 2. So the function tells me that this is 2 and this is 0. And I must plug in pi over 6. So pi divided by 6. And I get 2.6. Now it's a moment of truth. I have to make sure that these two rows work well together. If they don't, I'll go back to the drawing board, start from scratch. So from 2 to 2.6, what does the function do? From 2 to 2.6, what does the function do?
Increases.
Very good. Is that supported by the sign of the derivative?
Yep.
Perfect. What does the function do from 2.6 to 0? Good. Is that supported by the sign of the derivative?
Yes.
Perfect. So what type of point is 0, 2? Don't say anything before I just show you something in matter of points. So 0, 2 is here with a height of 2. Pi over 6, 2.6 is here. And pi over 2, 0 is here. Of course, I'm not graphing the function. I'm just plotting these points. So 0, 2 is here. Then pi over 6, 2.6 is here. And pi over 2, 0 is here. So what type of point is this?
Is it a relative min?
Nothing. It's at the end point of the interval. It can never be relative because it's at the end point of the interval. There are values higher than it, there are values lower than it. Is that clear?
Yep.
Perfect. Now let's see what this is. This point. Pi over 6, 2.6.
Relative mass.
Yes. But also And that's very important. Also what?
Absolute max.
Excellent. Perfect. Awesome. What about this one? Pi over 2 comma 0.
Absolute minimum.
Thank you very much. Very good. It cannot be relative, it's at the endpoint of the interval, but it's the smallest possible value of this function. So again, what have we learned so far? The first derivative gives increasing, decreasing intervals, and it gives us the relative max, relative min, also absolute max, absolute min. So max, min, increasing, decreasing. Any questions here? Any questions? Okay. I will not forget 4.2, but I don't want to stop. We have all the information we need to move on to 4.3. 4.2 is two theorems. Rawls theorem and the mean value theorem. They are related. We're going to talk about them after we finish graphing. These are just small applications. So at the beginning, where are my pages? Here. At the beginning today, I said graphing, this is what we're getting at, optimization and Newton's method. And there are in between just a tiny little bit of something else. So two theorems. We need 25 minutes for them, but I want to continue. And now I want to continue with the second derivative. So we know two things come from the first derivative, increasing, decreasing, max, min. What about the second derivative? And no, this is it. We're not going to move on to more. This is it, first and second derivative. What does this give? So two things come from the first derivative. What do we need and what do we learn from the second derivative? Okay. From the second derivative, we learned also two things. More, but two major things. Concavity. You can say, what is that? Here it is. The function on this side is concave down or downward. On this side is concave upward. So how is this related here? Well, when the second derivative is negative, the function is concave downward. When the second derivative is positive, the function is concave upward. So this is f of x. This is the graph of f of x. Concave down, concave up. Second derivative positive, concave up. Second derivative negative, concave down. And this is a very important point. This is called, and this is the second thing we learned from the second derivative, inflection point. What is an inflection point? Is the point where the function changes concavity. And of course, the derivative, the second derivative, changes sign. Exactly like with the first derivative. Or is undefined, of course. So, 0 or undefined and changes sign. It can change from negative to positive, or it can change from positive to negative. So the second derivative also gives us two important pieces of information about the function. If the second derivative is negative, the function is concave downward. If the second derivative is positive, the function is concave upward. So intervals of concavity, like the intervals of decreasing, increasing from the first derivative, right? And this is the inflection point. It's like the critical number. Same idea. Okay, just it gives us two different pieces of information, but the same concept, the same analysis. Okay, so now I would like us to, I'm going to share my screen and jump directly to 4.3. And now we can put everything together and we can graph. Okay, let's look at just a simple example here. We can choose any graph. I just would like to analyze this quickly. You choose any graph. Intervals of increasing, decreasing, concavity, and points of inflection. So choose a graph so we can discuss that.
One.
Okay. So obviously the function is concave upward. It has a minimum. Concave upward, yes, 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 till this point. This must be an inflection point because it changes concavity. It's now, we say it holds water, it does not hold water, it does not hold water. So concave up between 0 and 2, and all the way afterwards, only concave down. Where the function changes concavity from holding water to not holding water, this is the inflection point, which is 2, 3. Okay, so I would like us to choose this time a user-friendly function, something that we can follow through step by step. Find the intervals. So here it says find the intervals of increasing, decreasing, and local max, local min. This is what we just did. This is from 4.1. Find the intervals on which f is concave upward or concave downward. So this is what we want. So let's analyze an inflection point or points, and then or we can choose from the next set, but then I would like us to graph, if we still have time, 15 minutes, I would like us to graph a function from the beginning till the end.